CS50, and this is finally week 6, and this is that week we promised wherein we finally transitioned from C, this lower level, older language, via which we explored memory and how really computers work underneath the hood, to what's now called Python, which is a more modern, higher level language whereby we're still going to be able to solve the same types of problems, but it's going to suddenly start to get much, much easier because what Python offers, as do higher level languages more generally, are what we might describe as like abstractions over the very low level ideas that you've been implementing in sections and problem sets and so much more. But recall from week 0 where we began, this was our simplest of programs that just printed hello world. Things escalated quickly thereafter in week 1 where suddenly we had all of this new syntax, but the idea was still the same of just printing out hello world. Well, as of today, a lot of that distraction, a lot of the visual distraction goes away entirely, such that what used to be this in C will now be quite simply this in Python. And that's a bit of a head fake in that we're going to see some other fancier features of Python, but you'll find that Python's popularity in large part derives from just how relatively readable it is, and also, as we'll ultimately see, just how exciting and filled the ecosystem among Python programmers is. That is to say, there's a lot more libraries. There's a lot more problems that people have solved in Python that you can now incorporate into your own programs in order to stand on their shoulders and get real work done faster. But recall, though, from C that we had a few steps via which to actually compile that kind of code. So we got into the habit of make to make our program called hello, and then we've been in the habit of running it with /hello, the effect of which, of course, is to feed all of the zeros and ones that compose the hello program into the computer's memory and in turn the CPU. We revealed that what make is really doing is something a little more specific, namely running Clang, the C language compiler, specifically with some automatic command line arguments so as to output the name that you want, link in the library that you want, and so forth. But with Python, wonderfully, we're going to get rid of those steps too and quite simply run it as follows. Henceforth, our programs will no longer be in files ending in .c, suffice it to say. Our files starting today are going to start ending with .py, which is an indication to the computer, Mac OS, Windows, Linux, or anything else, that this is a Python program. But unlike C, wherein we've been in the habit of compiling our code and running it. Compiling our code and running it. Anytime you make a change, with Python, those two steps sort of get reduced into one, such that anytime you make a change and want to rerun your code, you don't explicitly compile it anymore. You instead just run a program called Python, similar in spirit to Clang. But whereas Clang is a compiler, Python we'll see is not only the name of the language, but the name of a program. And the type of that program is that of interpreter. An interpreter is a program that reads your code top to bottom, left to right, and really does what it says without having this intermediate step of first having to compile it in zeros and ones. So with that said, let me do this. Let me flip over here to VS Code. And within VS Code, let me write my first Python program. And as always, I can create a new file with the code command within VS Code. I'm going to create this file called hello.py, for instance. And quite simply, I'm going to go ahead and simply do print, quote unquote, hello world. And if I go down to my terminal window, instead of compiling this, I'm instead going to interpret this program by running Python space in the name of the file I want Python to interpret, hitting enter, and voila. Now you see hello world. But let me go ahead and compare this at left. Let me also go ahead and bring back briefly a file called hello.c. And I'm going to do this as we did in the very first day of C, where I included standard.io.h. I did int main void. I did inside of there printf, quote unquote, hello comma world \n close quote semicolon. And let me go ahead in VS Code. And if you drag your file over to the right or the left, you can actually split screen things if of help. And what I've done here is, and let me hide my terminal window, I've now compared these two files left and right. So here's hello.c from, say, week 1. Here's hello.py from week 6 now. And the differences are perhaps obvious, but there's a subtlety, at least one subtlety. Beyond getting rid of lots of syntax, what did I apparently omit from my Python version, even though it didn't appear to behave in any buggy way? Yeah. Sorry? The library. So I didn't actually have to include any kind of library like the standard IO library. Print, apparently in Python, just works. So I don't need to use main anymore. So this main function, to be clear, was required in C because that's what told the compiler what the main part of your program is. And you can't just start writing code otherwise. What else do you see? So there's no more semicolon, wonderfully enough, at the end of this line, even though there was here. And things are getting a little more subtle now. What else? So the new line. So recall that in printf, if you wanted to move the cursor to the next line when you're done printing, you had to do it yourself. So it seems as though Python, because when I interpreted this program a moment ago, the cursor did move to the next line on its own. They sort of reversed the default behavior. So those are just some of the salient differences here. One, you don't have to explicitly include standard libraries, so to speak, like standard IO. You don't need to define a main function anymore. You can just start writing your code. You don't need these parentheses, these curly braces. Printf is now called print, it would seem, and you don't need the \n. Now, there is one thing that's also a little looser, even though I didn't do it here. Even though in C, it was required to use double quotes anytime we want to use a string, aka char star. In Python, as with a lot of languages nowadays, you can actually get away with just using single quotes so long as you are consistent. Generally speaking, some people like this because you don't have to hold shift, and therefore you just hit one key instead of two. So there's an argument in terms of efficiency. However, if you want to use an apostrophe in your string, then you have to escape it. And so in general, stylistically, I'll use double quotes in this way. But things are getting a little looser now with Python, whereby that's not actually a requirement. But what's especially exciting with Python, and really a lot of higher level languages, is just how much real work you can get done relatively quickly. So you've just spent quite a bit of time, dare say, implementing your spell checker and implementing your own dictionary of sorts. Well, let me propose that maybe we should have asked you to do that in Python instead of C. Why? Well, let me go ahead and do this. Let me close these two tabs and reopen my terminal window. Let me go into a directory called Speller that I downloaded in advance. For class. And if I type ls in here, you'll notice that it's very similar to what you spent time on with problem set 5, but the file extensions are different. There's a dictionary.py instead of dictionary.c. There's a speller.py instead of a speller.c. And there's the exact same directories, dictionaries and texts, that we gave you for problem set 5. So let me just stipulate that I spent time implementing speller.c in Python. And so I gave it a name of speller.py. But I didn't go about really implementing dictionary.py yet. And so why don't we go ahead and actually implement dictionary.py together by doing this. Let me clear my terminal, do code dictionary.py, and let me propose that we implement ultimately 4 functions. And what are those functions going to be? Well, they're going to be the check function, the load function, the size function, and the unload function. But recall that in problem set 5, you implemented your own hash table. And so while there isn't a hash table data type in Python, I'm going to go ahead and do this. I'm going to create a variable, a global variable in dictionary.py called words, and I'm going to make it a set. in the mathematical sense. A set is a collection of things that won't contain duplicates. Any duplicates will be filtered out. So I'm going to now, after that, creating that one global variable, I'm going to create a function called check, just as you did. And check takes as input a word. And if I want to check if a word is in that set of words, I can simply do word.lower in words. And that's it. Let me now define another function called load, which recall took an argument, which was the name of the dictionary you want to load into memory. Inside of my load function, I'm now going to do this. I'm going to say with open dictionary as a variable called file. And in there, I'm going to go ahead and update the set of words to be the updated version of whatever's in this file as a result of reading it and then splitting its lines, whereby this file has a big, long column of words, each of which is separated by a new line. Split line is going to split all of those into one big collection. And then I'm just going to go ahead and return true. I'm now going to go ahead and define a size function just as you did. But in Python, I'm going to go ahead and return the length of that set of words, where length, or len, is a function itself in Python. And I'm going to do one last function. It turns out that in Python, even though for this program I'm going to go and implement a function called unload, there's not actually anything to unload in Python because Python will manage your memory for you. Malloc is gone. Free is gone. Pointers are gone. It handles all of that seemingly magically for now for you. So here then is I claim what you could have done with problem set 5 if implementing it in Python instead. Let me go ahead and open my terminal window. Let me increase its size. Let me run Python of speller.py, which is the name of the actual program, not the dictionary per se that I implemented. Let's run it on a file called homes.txt because that was a particularly big file. And if I hit enter now, we'll see hopefully the same output that you saw in C flying across the screen. And eventually, we should see that same summary at the bottom as to how many words seem to be misspelled, how many words were in the dictionary, and ultimately how fast this whole process was. Now, the total amount of time required was 1.93 seconds, which was actually longer than it seemed to take. That's because we're doing this in the cloud, and it was taking some amount of time to send all of the text to my screen, but the code was only taking 1.93 seconds total on the actual server. And hopefully these same kinds of numbers line up with your own. The difference being what I did not have to implement for this spell checker is your own hash table, is your own dictionary, literally beyond what I've done using Python here with some of these built-in features. So why use C? Why not always use Python, assuming that you prefer the idea of being able to whip up within seconds the entirety of problem set 5? How might you choose now between languages? And I apologize if you're harboring resentment that this wasn't a week earlier. Why Python or why C? Any instincts? Any thoughts? Just hopefully a reason. Yeah, over here. Yeah. Really good conjecture. So you always thought that Python was slower than C and takes up more space than C. Odds are that's in fact correct. So even though ultimately this 1.93 seconds is still pretty darn fast, odds are it's a little slower than the C version would have been. It's possible, too, that my version in Python actually does take up more RAM or memory underneath the hood. Why? Well, because Python itself is managing memory for you, and it doesn't necessarily know a priori how much memory you're going to need. You, the programmer, might, and you, the programmer writing in C, allocated presumably exactly as much memory as you might have needed last week with problem set 5. But Python's got to maybe do its best effort for you and try to manage memory for you. And there's going to be some overhead. The fact that I have so many fewer lines of code, the fact that these lines of code sort of solve problem set 5 for me means that Python, or whoever invented Python, they wrote lines of code to sort of give me this functionality. And so if you think of Python as a middleman of sorts, it's doing more work for me. It's doing more of the heavy lift. So it might take me a bit more time, but my gosh, look how much time it has saved in terms of writing this code more quickly. And arguably, this code is even more readable, or at least will be after today, week 6, once you have an eye for the syntax and features of Python itself. So beyond that, it turns out you can do other things pretty easily as well. Let me go back into my terminal window. Let me close this dictionary.py. Let me go into a folder called filter, in which I have this same bridge that we've seen in the past across the river there. So here's a a bridge. This is the original version of this particular photograph. Suppose I actually want to write a program that blurs this. Well, you might recall from problem set 4, you could write that same code in C by manipulating all of the red, the green, the blue pixels that are ultimately composing that file. But let me go ahead and propose this instead. Let me create a file called blur.py. And in this file, let me go ahead and import a library. So from the Python image library, PIL, let me go ahead and import something called image, capital I, and image filter, capital I, capital F. So I'm going to do before equals image.open, quote unquote, bridge.bmp. Then let me go ahead and create another variable called after and set that equal to before.filter, and then in parentheses, image filter, spelled as before, dot box blur, and then we'll give it a value of 10. How much do I want to blur it, for instance? After that, I'm going to literally call after.save, and let's save it as a file called out.bmp. And that's it. I propose that this is how you can now write code in Python to blur an image, much like you might have for problem set 4. Now let me go ahead in my terminal window and run Python of blur.py. When I hit enter, those 4 lines of code will run. It seems to have happened quite quickly. Let me go ahead and open now out.bmp. And whereas the previous image looked like this a moment ago, let me go ahead and open out.bmp. And hopefully you can indeed see that it blurred it for me using that same code. And if we want things to escalate a little more quickly, let me go ahead and do this instead. Let me close blur.bmp. Let me go ahead and open a file called edges.py. And maybe in edges.py, we can use this same library. So from the Python image library, import image and import image filter. Let me go ahead and create another variable called before, set it equal to image.open, quote unquote, bridge.bmp, just like before. Let me create another variable called after, set that equal to before.filter, image filter.find edges, which comes with this library automatically. And lastly, the same thing. Save this as a file called out.bmp. So if you struggled perhaps with this one previously, whereby you wrote for the more comfortable version of problem set 4 edge detection, so to speak, well, you might have then created a file that, given an input like this, the original bridge.bmp, this new version, out.bmp, with just 4 lines of code, now looks like this. So again, if this is a little frustrating that we had you do all of this in C, that was sort of exactly the point, to motivate that you now understand nonetheless what's going on underneath the hood. But with Python, you can express these solutions to problems all the more efficiently, all the more readily. And just one last one, too. It's very common nowadays in the world of photography and social media and the like to do face detection, for better or for worse. And it turns out that face detection, even if you want to integrate it into your own application, is something that lots of other people have integrated into their applications as well. So Python, to my point earlier of having this very rich ecosystem of libraries that other people wrote, you can literally run a command like pip install face_recognition if you want to add support to your code space or to your programming environment more generally for the notion of face recognition. In fact, this is going to automatically install from some server elsewhere a library that someone else wrote called face recognition. And with this library, you can do something like this. Let me go into a directory that I came with in advance. Let me go ahead and ls in there, and you'll see 4 files, detect.py and recognize.py, which are going to detect faces and then recognize specific faces, respectively. And then 2 files I brought from a popular TV show, for instance. So if I open office.jpg, here is one of the early cast photos from the hit TV series, The Office. And here is a photograph of someone specific from the show, Toby. Now, this is, of course, Toby's face. But what is it that makes Toby's face a face? More Generally, if I open up office.jpg and I asked you, the human, to identify all of the faces in this picture, it wouldn't be that hard with a marker to sort of circle all of the faces. But how? Why? How do you, as humans, detect faces, might you think? Yeah. Features, yeah, like eyes, nose, generally in a similar orientation, even though we all have different faces ultimately. But there's a pattern to the sort of to the shapes that you're seeing on the screen. Well, it turns out this face recognition library has been trained, perhaps via artificial intelligence over time, to recognize faces, but any number of different faces, perhaps among these folks here. So if I go back into my terminal window here, let me go ahead and run say Python of detect.py, which I wrote in advance, which uses that library. And what that program's going to do, it's going to do some thinking. It's just found some face. And let me go ahead now and open a file it just created called detected.jpg, which I didn't have in my folder a moment ago. But when I open this here file, you'll now see all of the faces based on this library's detection thereof. But suppose that we're looking for a very specific face among them, maybe Toby's. Well, maybe if we write a program that doesn't just take as input the office.jpg, but a second input, toby.jpg, maybe this library, and code more generally, can distinguish Toby's face from Jim's, from Pam's, from everyone else in the show, just based on this one piece of training data, so to speak. Well, let me instead run Python of recognize.py and hit enter. It's going to do some thinking, and it is going to output now a file called recognized.jpg, which should show me his face ideally specifically. And so what has it done? Well, with sort of a green marker, there is Toby among all of these faces. That's maybe a dozen or so lines of code. There is really specifically JPEG, which should show me his face ideally specifically. And so what has it done? Show me his face ideally specifically. And so what has it done? Well, with sort of a green marker, there is Toby among all of these faces. That's maybe a dozen or so lines of code, but it's built on top of this ecosystem of libraries. And this is, again, just one of the reasons why Python is so popular. Undoubtedly, some number of years from now, Python will be out and something else will be back in. But that's indeed among the goals of CS52, is not to teach you C, not to teach you Python, not in a couple of weeks to teach you JavaScript and other languages too, but to teach you how to program. And indeed, all of the ideas we have explored and will now explore more today, you'll see recurring for languages in the years to come. Any questions before we now dive into how it is this code is working and why I typed the things that I did before we forge ahead? Any questions along these lines? Anything at all? No? All right. So how does Python itself work? Well, let's do a quick review as we did when we transitioned from Scratch to C, this time, though, from Scratch, say, to Python. So in In Python, as with many languages, there are these things called functions, the actions and verbs that actually get things done. So here on the left, recall from week 0, was the simplest of functions we played with first, the say block, which just literally has the cat say something on the screen. We've seen in C, for instance, the equivalent line of code is arguably this here with printf, with the parentheses, the quotation marks, the \n, the semicolon. In Python now, it's going to indeed be a little simpler than that. But the idea is the same as it was back in week 0. Libraries. So we've seen already in C, and now we've already seen in Python that these things exist too. In the world of C, recall that besides the standard ones, like standard io.h, that header file, we very quickly introduced cs50.h, which was like your entry point, the header file for the cs50 library, which gave you a bunch of functions as well. Well, we're going to give you a similar library for at least the next week or two, training wheels for Python specifically, that again will take off so that you can stand on your own, even with cs50 behind you. But the syntax for using a library in Python is a little different. You don't include a .h file. You just import instead the name of the library. All right, what does that actually mean? Well, if there are specific functions in that library you want to use, in Python you can be more precise. You don't just have to say, give me the whole library. For efficiency purposes, you can say, let me import the getString function from the CS50 library. So you have finer grained control in Python, which can actually speed things up if you're not loading things unnecessarily into memory, if all you want is, say, one feature therein. So here, for instance, in Scratch, was an example of how we might use not only a built-in function like the say block, or in C in the printf, but how we might similarly now do the same but achieve this in Python. So how might we do this? Well, in Python, or rather in C, this code looked a little something like this back in week 1. We declared a variable of type string, even though later we revealed that to be char star. I gave this a variable name of answer for parity with Scratch. Then we used CS50's own getString function and asked, for instance, the same question as in the white oval here. And then using this placeholder syntax, these format codes, which was printf specific, we could plug in that answer to this pre-made string where the %s is. And we saw %i and %f and a bunch of others as well. So this is sort of how in C you approximate the idea of concatenating two things together, joining two things, just as we did here in Scratch. So in Python, it turns out it's not only going to be a little easier, but there's going to be even more ways to do this. And so even what might seem today like a lot of different syntax, it really is just different ways stylistically to achieve the same goals. And over time, as you get more comfortable with this, you too will develop your own style, or if working for a company or working with a team, you might collectively decide which conventions you want to use. But here, for instance, is one way you could implement this same idea in Scratch, but in Python instead. So notice I'm going to still use a variable called answer. I'm going to use CS50's function called getString. I'm still going to use quote unquote what's your name, but down here is where we see the most difference. It's again not called printf in Python. It's now called just print. And what might you infer the plus operator is doing here? It's not addition, obviously, in a mathematical sense. But those of you who have perhaps programmed before, what does the plus represent in this context? It's indeed joining the two strings together. So this is indeed concatenating the thing on the left with the thing on the right. So you don't use the placeholder in this particular scenario. You can instead, a little more simply, just use plus. But you want your grammar to line up. So I still have HELLO, comma, space, and then close quote, because I want to form a full phrase. Notice, too, there's also one other slightly more subtle difference on the first line. Besides the fact that we don't have a semicolon, what else is different? I didn't declare the type of the variable. So Python still has strings, as we'll see, but you don't have to tell the interpreter what type of variable it is. And this is going to save us some keystrokes, and it's just going to be a little more user-friendly over time. Meanwhile, you can do this also a little bit differently if you prefer. You can instead trust that the print function in Python can actually do even more for you automatically. The print function in Python can take multiple arguments separated by commas in the usual way. And by default, Python is going to insert for you a single space between its first argument and its second argument. So notice what I've done here is my first argument is quote unquote hello with a comma, but no space. Then outside of the quotes, I'm putting a comma, because that just means here comes my second argument. And then I put the same variable as before. And I'm just going to let Python figure out that it should, by default, per its documentation, join these two variables putting a single space in between them. Can do this yet another way, and this way looks a little weirder, but this is actually probably the most common way nowadays in Python, is to use what's called a format string, or F string for short. And this looks weird. To me still, it looks weird. But if you prefix a string in Python with an F, literally, you can then use curly braces inside of that string in Python. And Python will not print out literally a curly brace and a closed curly brace. It will instead interpolate whatever is inside of those curly braces. That is to say, if answer is a variable that has some value, like David or something like that, saying F before the first quotation mark and then using these curly braces therein is going to do the exact same thing of creating a string that says hello, comma, space, David. So it's going to plug in the value for you. So you can kind of think of this as %s, but without that second step of having to like keep track of what you want to plug back in for %s. Instead of %s, you literally put in curly braces, what do you want to put right there? You format the string yourself. So given all of those ways, how might we actually go about implementing this or using this ourselves? Well, let me propose that we do this here. Let me propose that I go back to VS Code. Let me go ahead and open up hello.py again. And as before, instead of just printing out something like quote unquote hello world, let me actually print out something a little more interesting. So let me go ahead and from the CS50 library import the function called getString. Then let me go ahead and create a variable called answer. Let me set that equal to the return value of getString with, as an argument, quote unquote, what's your name, question mark. And then no semicolon at the end of that line. But on the next line, frankly, here, I can pick any one of those potential solutions. So let me start with the first. So hello, comma, space, quote, plus answer. And now if I go down to my terminal window and run python of hello.py, I'm prompted for my name. I can type in DAVID, and voila, that there then works. Or I can tweak this a little bit. I can trust that Python will concatenate its first and second argument for me, but this isn't quite right. Let me go ahead and rerun python of hello.py, hit enter, and type in David. It's going to be ever so slightly buggy, sort of grammatically or visually, if you will. What did I do wrong here? Yeah, so I left the space in there, even though I'm getting one for free from print. So that's an easy solution here. But let's do it one other way after running this to be sure. DAVID. And OK, now it looks like I intended. Well, let's go ahead and use that placeholder syntax. So let's just pass in one bigger string as our argument. Do hello, comma, and then in curly braces, answer, like this. Well, let me go down to my terminal window and clear it. Let me run python of hello.py and enter, type in DAVID, and voila. OK, I made a mistake. What did I do wrong here? Minor, though it seems to be. Yeah. So the stupid little f that you have to put before the string to tell Python that this is a special string, it's a format string or f string that it should additionally format for you. So if I rerun this after adding that f, I can do python of hello.py, what's your name, David, and now it looks the way I might intend. But it turns out in Python, you don't actually need to use getString. In C, recall that we introduced that because it's actually pretty annoying in C to get strings, in particular to get strings safely. Recall those short examples we did with scanf not too long ago. And scanf kind of scans what the user types at the keyboard and loads it into memory. But the fundamental danger with scanf when it comes to strings was what? Why was it dangerous to use scanf to get strings from a user? Why? Yeah. Exactly. What if they give you a really long string that you didn't allocate space for because you're not going to know as the programmer in advance how long of a string the human is going to type in. So you might undercut it and therefore have too much memory too many characters being put into that memory, thereby giving you some kind of buffer overflow, which might crash the computer or minimally your program. So it turns out in C, getString was especially useful. In Python, it's not really that useful. All it does is use a function that does come with Python called input. And in fact, the input function in Python, for all intents and purposes, is the same as the getString function that we give to you. But just to ease the transition from C to Python, we implemented a Python version of getString nonetheless. But this is to say, if I go to VS Code here and I just change getString to input. And in fact, I even get rid of the CS50 library at the top. This too should work fine. If I rerun python hello.py, type in my name David, and voila, I have that now working as well. All right, questions about this use of getString or input or any of our syntax thus far? No? All right, well, what about variables? We've used variables already, and we already identified the fact that you don't have to specify the type of your variables proactively, even though clearly Python supports strings thus far. Well, in Python, here's how you might declare a variable that not necessarily is assigned like a string, but maybe an integer instead. So in Scratch, here's how you could create a variable called counter, if you want to count things, and set it equal to 0. In C, what we would have done is this: int counter equals 0, semicolon. That's the exact same thing as in Scratch. But in Python, as you might imagine, we can chip away at this and type out this same idea a little more easily. 1, we don't need to say int anymore. 2, we don't need the semicolon anymore. And so you just do what you intend. If you want a variable, just write it out. If you want to assign it a value, you use the equal sign. If you want to specify that value, you put it on the right. And just as in C, this is not the equality operator, it's the assignment operator from right to left. Recall that in Scratch, if you wanted to increment a variable by 1 or any value, you could use this puzzle piece here. Well, in C, you could do syntax like this, which again is not equality. It's saying add 1 to counter and then assign it back to the counter variable. In Python, you can do exactly the same thing minus the semicolon. So you don't need to use the semicolon here, but you might recall that in C there was some syntactic sugar for this idea because it was pretty popular, and so you could shorten this in C, as you can in Python, to actually just this. Plus equals 1 will add to the counter variable whatever that value is. But it's not all steps forward. You might be in the habit of using plus plus or minus minus. Sorry, those are not available in Python. Why? It's because the designers of Python decided that you don't need them because this gets the job done anyway. But there's a question down here in front, unless it was about the same. All right, so that's one feature we're taking away, but it's not such a big deal to do plus equal in this case. Well, what about the actual types involved here beyond actually being able to define variables? Well, recall that in the world of C, we had at least these data types, those that came with the language in particular, and we played with quite a few of these over time. In Python, we're going to take a bunch of those away. In Python, you're only going to have access to a bool, true or false, a float, which is a real number with a decimal point typically, an int or an integer, and a string, now known as str. So Python here sort of cuts some corners, feels like it's too long to write out strings. So a string in Python is called str, S-T-R, but it's the exact same idea. Notice, though, that missing from this now, in particular, are double and long, which recall actually used more bits in order to store information. We'll see that that might not necessarily be a bad thing. In fact, Python just simplifies the world into 2 different types of variables, but gets out of the business of you having to decide, do you want like a small int or a large int or something along those lines? Well, let me go ahead and do this. Let me switch back over to VS Code here. And why don't we actually try to play around with some calculations using these data types and more? Let me go ahead and propose that we implement, like we did way back in week 1, a simple calculator. So let me do this. Code of calculator.c. So I'm indeed going to do this in C first, just so that we have a similar example at hand. So I'm going to include standard io.h here on the, at the top. I'm going to go ahead and do int main void. Inside of main, I'm going to go ahead and declare a variable called x and set that equal to getInt. And I'm going to prompt the user for that value x. But if I'm using getInt, recall that actually is from the CS50 library. So in C, I'm going to need cs50.h still for this example. But back in week 1, I then did something else. I then said, give me another variable called y, set that equal to getInt, and set that equal to that, pass in that prompt there. And then lastly, let's just do something super simple like add 2 numbers together. So in C, I'll use printf. I'm going to go ahead and do %i\n as a placeholder. And then I'm just going to plug in x plus y. So all of that that was in C. So it was a decent number of lines of code to accomplish that task, only 3 of which are really the logical part of my program. Like these are the 3 that we're really interested in. So let me instead now do this. Code of calculator.py, which is going to give me a new tab. Let me just drag it over to the right so I can view these side by side. And in calculator.py, let's do this. From the CS50 library, import the getInt function, which is also available. Then let's go ahead and create a variable called x and set it equal to the return value of getInt, passing in the same prompt. No semicolon, no mention of int. Let's then create a second variable y, set it equal to getInt, prompt the user for y as before. No int, explicitly no semicolon. And now let's just go ahead and print out x plus y. So it turns out that the print function in Python is further flexible, that you don't need these format strings. If you want to print out an integer, just pass it an integer, even if that integer is the sum of two other integers. So it just sort of works as you might expect. So let me go down into my terminal here. Let me run Python of calculator.py. And when I hit enter, I'm prompted for x. Let's do 1. I'm prompted for y. Let's do 2. And voila, I should see 3 as the result. So no actual surprises there. But let me go ahead and, you know what, let's take away this training wheel, right? We don't want to keep introducing CS50 specific things. So suppose we didn't give you getInt. Well, it turns out that getInt is still doing a bit of help for you, even though getString was kind of a throwaway. And we could replace getString with input. So let's try the same idea. Let's go ahead and prompt the user for input for both x and y using the input function in Python instead of getInt from CS50. Let me go ahead and rerun Python of calculator.py and hit enter. So far, so good. Let me type in 1. Let me type in 2. And what answer should we see? Hopefully still 3, but nope. Now the answer is 12. Or is it? Why am I seeing 12 and not 3? Yeah, so it's actually concatenating what seem to be two strings. So if we actually read the documentation for the input function, it's behaving exactly as it's supposed to. It is getting input from the user from their keyboard. But anything you type at the keyboard is effectively a string. Even if some of the symbols happen to look like or actually be decimal numbers, they're still going to come to you as strings. And so x is a string, aka stir. Y is a stir. And we've already seen that if you use plus in between two strings or stirs, you're going to get concatenation, not addition. So you're not seeing 12 as much as you're seeing 1, 2, not 12. So how can we fix this? Well, in C, we had this technique where we could cast one thing to another by just putting like int in parentheses, for instance. In Python, things are a little higher level such that you can't quite get away with just casting one thing to another, because a string, recall, is not the same thing as a char. A string has 0 or more characters. A char always has 1. And in C, there was a perfect mapping between single characters and single numbers in decimal, like 65 for capital A. But in Python, we can do something somewhat similar and not so much cast, but convert this input to an int and convert this input to an int. So just like in C, you can nest functions. You can call one function and pass its output as the input to another function. And this now will convert x and y to integers. And so now plus is going to behave as you would expect. Let me rerun Python of calculator.py, type in 1, type in 2, and now we're back to seeing 3 as the result. If this is a little unclear, this nesting, let me do this one other way. Instead of just passing inputs, output into int, I could also more pedantically do this. X should actually equal int of x. Y should actually equal int of y. This would be the exact same effect. It's just like 2 extra lines where it's not really necessary, but that would work fine. If you don't like that approach, we could even do it inline. We could actually convert x to an int and y to an int. Why? Well, int, int, in the context of Python itself is a function. And it takes as input here a string or a stir and returns to you the numeric, the integral equivalent. So similar idea, but it's actually a function. So all of the syntax that I've been tinkering with here is sort of fundamentally the same as it would be in C. But in this case, we're not casting, but converting more specifically. Well, let me go back to these data types. These are some of the data types that are available to us in Python. Turns out there's a bunch of others as well that we'll start to dabble with today. You can get a range of values, a list of values, which is going to be like an array, but better. Tuples, which are kind of like x comma y, often combinations of values that don't change. Dict for dictionary. It turns out that in Python, you get dictionaries. You get hash tables for free. They're built into the language. And we already saw that Python also gives you a data type known as a set, which is just a collection of values that gives you, gets rid of any duplicates for you. And as we saw briefly in Speller, and we'll play more with these ideas soon, it's going to actually be pretty darn easy to get values or check for values in those their data types. So that in C, we were able to get input easily. We had all of these functions. In the CS50 library for Python, we're only going to give you these instead. They're going to be the same name, so it's still getString, not getStir, because we wanted the functions to remain named the same. But getFloat, getInt, getString all exist. But again, getString is not all that useful. But getInt and getFloat actually are. Why? Well, let me go back to VS Code here. And let me go back to the second version of this program whereby I proactively converted each of these return values to integers. So recall that this is the solution to the 1, 2 problem. And to be clear, if I run Python of calculator.py and input 1 and 2, I get back now 3 as expected. But what I'm not showing you is that there's still potentially a bug here. Let me run Python of calculator.py, and let me just not cooperate. Instead of typing what looks like a number, let me actually type something that's clearly a string like cat. And unfortunately, we're going to see the first of our errors, the first of our runtime errors. And this, like in C, is going to look cryptic at first, but this is generally known as a traceback, where it's going to trace back for you everything your program just did, even though this one's relatively short. And you'll see that calculator.py, line 1, I didn't even get very far before there's an error. And then with all of these caret symbols here, like this is a problem. Why? Invalid literal for int function with base 10, quote unquote cat. Again, just like in C, it's very arcane. It's hard to understand this the first time you read it. But what it's trying to tell me is that cat is not an integer. And therefore, the int function cannot convert it to an integer for you. We're going to leave this problem alone for now. But this is why, again, getInt's looking kind of good and getFloat's looking kind of good, because those functions from CS50's library will deal with these kinds of problems for you. Now, just so you've seen it, there's another way to import functions from these things. If you were to use, for instance, in a program, getFloat, getInt, and getString, you don't need to do 3 separate lines like this. You can actually separate them a little more cleanly with commas. And in fact, if I go back to a version of this program here in VS Code whereby I actually do use the getInt function. So let me actually get rid of all this and use getInt as before. Let me get rid of all this and use getInt as before. Previously, the way I did this was by saying from CS50 import getInt, if you know in advance what function you want to use. But suppose, for whatever reason, you already have your own function named getInt, and therefore it would collide with CS50's own. You can avoid that issue, too, by just using that first statement we saw earlier. Just import the library itself. Don't specify explicitly which functions you're going to use. But thereafter, and you could not do this in C, you could specify cs50.getInt, cs50.getInt in order to go into the library, access its getInt function, and therefore it doesn't matter if you or any number of other people wrote an identically named function called getInt, you're using here clearly CS50's own. So this is, again, just more ways to achieve the same solution, but with different syntax. All right, any questions about any of this syntax or features thus far? No? All right, well, how about maybe another example here whereby we revisit conditionals, which was the way of implementing do this thing or this thing, sort of proverbial forks in the road. In Scratch, recall, we might use building blocks like these to just check, is x less than y? And if so, say so. In C, this code looked like this. And notice that we had parentheses around the x and the y. We had curly braces, even though I did disclaim that for single lines of code, you can actually omit the curly braces. But stylistically, we always include them in CS50's code. But you have the \n and the semicolon. In a moment, you're about to see the Python equivalent of this, which is almost the same. It's just a little nicer. This, then, is the Python equivalent thereof. So what's different at a glance here, just to be clear? What's different? Yeah. So the conditional is not in parentheses. You can use parentheses, especially if logically you need to group things. But if you don't need them, don't use them, is Python's mindset. What else has changed here? Yeah. No curly braces, yes, so no curly braces around this. And even though it's one line of code, you just don't use curly braces at all. Why? Because in Python, indentation is actually really, really important. And we know from office hours and problem sets occasionally that, you know, if you forgot to run style 50 or you didn't manually format your code beautifully, you know, C is not actually going to care if everything is aligned on the left. If you never once hit the tab character or the space bar, C, or specifically Clang, isn't really going to care, but your teaching fellow, your TA is going to care, or your colleague in the real world, because your code's just a mess and hard to read. Python, though, because you are not the only ones in the world that might have bad habits when it comes to style, Python as a language decided, that's it, like everyone has to indent in order for their code to even work. So the convention is Python is to use 4 spaces, so 1, 2, 3, 4, or hit tab and let it automatically convert to the same, and use a colon instead of the curly braces, for instance, to make clear what is associated with this particular conditional. We can omit, though, the \n for per before. We can omit the semicolon, but this is essentially the Python version thereof. Here in C, in Scratch, if you wanted to do an if-else like we did back in week 0, in C, it's very similar to the if, except you add the else clause and write out an additional printf like this. In Python, we can tighten this up. If x less than y, colon, that's exactly the same. First line's the same. All we're doing now is adding an else and the second print line here. How about in Scratch? If we had a three-way fork in the road, if, else, in C, it looked pretty much like that. If, else. In Python, we can tighten this up. And this is not a typo. What jumps out at you as weird, but you got to just get used to it? Yeah. elif. And honestly, like years later, I still can't remember if it's elif or else if, because other languages actually do ELSIF. And now I probably now biased all of you to now questioning this, but it's elif in Python. ELIF is not a typo. It's in the spirit of let's just save ourselves some keystrokes. So elif is identical to else if, but it's a little tighter to type it this way. All right, so if we now have this ability to express conditionals, what can we actually do with them? Well, let me go over to VS Code here. And let me propose that we revisit maybe another program from before where we just compare two integers in particular. So I'm in VS Code. Let me open up a file called, say, compare.py. And in compare.py, we'll use the CS50 library just so we don't risk any errors, like if the human doesn't type an integer. So we're going to go ahead and say from CS50 import getInt. And in compare.py, let's get two variables, x equals getInt, and prompt the user for x. So what's x question mark? To be a bit more verbose, y equals getInt, quote unquote, what's y question mark? And then let's go ahead and just compare these two values. So if x is less than y, then go ahead and print out with print x is less than y, close quote. Elif x is greater than y, go ahead and print out x is greater than y, close quote. Else, go ahead and print out x is equal to y. So the exact same program, but I've added to the mix getting a value of x and y. Let me run Python of compare.py, enter. Let's type in 1 for x, 2 for y, x is less than y. Let's run it once more. X is 2, y is 1, x is greater than y. And just for good measure, let's run it a third time. X is 1, y is 1, x is equal to y. So the code, dare say, works exactly as you would expect, as you would hope. But it turns out that in the world of Python, we're actually going to get some other behavior that might actually have been what you expected weeks ago, even though C did not behave this way. In the world of Python and in the world of strings, aka strs, strings actually behave more like you would expect. So by that, I mean this. Let me actually go back to this code. And instead of using integers, let me go ahead and get rid of, I could do get string, but we said that that's not really necessary. So let's just go ahead and change this to input. And actually, you know what, let's just start fresh. Let's give myself a string called s and use the input function and ask the user for s. Let's use another variable called t, just because it comes after s, and use the input function to get t. Then let's compare if s and t are the same. Now, a couple weeks ago, this backfired. And if I tried to compare two strings for equality, it did not work. But if I do if s equals t, print quote unquote same, else let's go ahead and print different, I dare say in Python, I think this is going to work as you would expect. So Python of compare.py, let's type in cat and cat. And indeed, those are the same. Let me run it again and type in cat and dog, respectively. And those are now different. But in C, we always got different, different, different. Even if I type the exact same word, be it cat or dog or hi or anything else. Why in C were S and T always different a couple weeks ago? Yeah?
Because it was comparing the value of the char star, which is a memory address.
Exactly. In C, string is the same thing as char star, which is a memory address. And because we had called getString twice, even if the human typed the same things, that was two different chunks of memory at two different addresses. So those two char stars were just naturally always different, even if the characters at those addresses were the same. Python is meant to be higher level. It's meant to be a little more intuitive. It's meant to be more accessible to folks who might not necessarily know or want to understand those lower level details. So in Python, equals equals, even for strings, just works the way that you might expect. But in Python, we can do some other things too, even more easily than we could in C. Let me go back to VS Code here. Let me close compare.py, and let's re-implement a program from C called agree, which allowed us to prompt the user for like a yes/no question, like do you agree to these terms and conditions, or something like that. So let's do code of agree.py. And with agree.py, let me go ahead and actually, let's go ahead and do this. Let me also open up a file that I came with in advance. And this is called agree.c. And this is what we did some weeks ago when we wanted to check whether or not the user had agreed to something or not. So we used the CS50 library, the standard IO library. We had a main function. We used getChar. And then we used equals equals a lot. And we used the two vertical bars, which meant logical OR. Is this thing true, or is this thing true? And if so, printf agreed or not agreed. So this worked. And this is relatively simple. That's like the right way to do it in C. But notice it was a little verbose because we wanted to handle uppercase and lowercase, uppercase and lowercase. So that did start to bloat the code, admittedly. So let's try to do the same thing in Python and see what we can do the same or different. No pun intended. So let me do this. In agree.py, why don't we try to get input from the user as before? And I could use getString, but I'll go ahead and use input. So s equals input, do you agree, question mark, in double quotes. And then let's go ahead and check. If s equals equals capital Y, and it's not vertical bar now, it's actually more readable, more English-like, or s equals equals lowercase y, then go ahead and print out agreed, as before. Else if, see I did it there, if s equals equals capital N, or s equals equals lowercase n, go ahead and print out not agreed. So it's almost the same as the C version, except that I'm using literally OR instead of 2 vertical bars. So let's run this. So Python of agree.py, enter. Do I agree? Yes, for little y. Let's do it again. Python of agree.py, capital Y. Yes, that works there. And if I do it again with lowercase n, and if I do it with capital N, this program too seems to work. But what if I do this? Let me rerun Python of agree.py. Let me type in yes. OK, it just ignores me. Let me run it again. Let me type in no. Just ignores me. Let me try it very emphatically. Yes, in all caps. It just ignores me. So there's some explosion of possibilities that ideally we should handle. Right? This is bad user interface design. If the user has to type Y or N, even if yes and no in English are perfectly reasonable and logical too. So how could we handle that? Well, it turns out in Python, we can use something like an array, technically called a list, to maybe check a bunch of things at once. So let me do this. Let me instead say not equality, but let me use the in keyword in Python and check if it's in a collection of possible values. Let me say if s is in, and here comes in square brackets, just like in square brackets, quote unquote y, comma, quote unquote yes, then we can go ahead and print out agreed. If s is in this list of values, lowercase n or lowercase no, then we can print out, for instance, not agreed. But this is a bit of a step backwards because now I'm only handling lowercase. So let me go into the mix and maybe add capital Y. Wait a minute, then maybe capital yes, then maybe yes also. I mean, weird, but we should probably support this and like yes. I mean, there's like a lot of combinations. So this is not going to end well, or it's just going to bloat my code unnecessarily. And eventually, for longer words, I'm surely going to miss capitalization. So logically, whether it's in Python or C or any language, what might be a better design for this problem of handling Y and yes, but who cares about the capitalization? So don't use capitals. You could only support lowercase. That's fine. That's kind of a cop-out, right? Because now like the program's usability is worse. Oh, so we could convert it to lowercase. Yeah, though I did hear you say we could just check the first letter. I bet that's going to get us into trouble. And we probably don't want to allow any words starting with Y, any word starting with N, just because logically, especially you want like the lawyers happy, presumably you should probably get an explicit semantically correct word like Y or N or yes or no. But yeah, we can actually go about converting this to something maybe smaller. But how do we go about converting this? In C, that alone was going to be pretty darn annoying because we'd have to sort of use the to lower function on every character and compare it for equality. Just feels like that's a bit of work. But in Python, you're going to get more functionality for free. So there might very well be a function like in C called to lower or to upper. But the weird thing about C, perhaps in retrospect, is that those functions just kind of worked on the honor system. To lower and to upper just trusted that you would pass them an input, an argument that is in fact a char. In Python and in a lot of other higher level languages, they introduced this notion of object-oriented programming, which is commonly described as OOP. And in the world of object-oriented programming,